Section 7.4, metallic bonds and the properties of metals. The objectives are to describe a metallic bond, relate the electron C model to the physical properties of metals, define alloys and characterize them in two basic types. Some vocabulary review will be physical property, and some new vocabulary you'll come across is the electron C model, delocalized electron, metallic bond, and alloy. Although metals are not ionic, they share several properties with ionic compounds. The bonding in both metals and ionic compounds is based on the attraction of particles with unlike charges. Metals often form lattices in the solid state. These lattices are similar to the ionic crystal lattice discussed earlier. In such a lattice, 8 to 12 other metal atoms closely surround each metal atom. Although metal atoms always have at least one valence electron, they do not share these valence electrons with neighboring atoms, nor do they lose their valence electrons. Instead, within the crowded lattice, the outer energy levels of the metal atoms overlap. This unique arrangement is described by the electron C model. The electron C model proposes that all the metal atoms in a metallic solid contribute their valence electrons to form a sea of electrons. This sea of electrons surrounds the metal cation in the lattice. The electrons present in the outer energy levels of the bonding metallic atoms are not held by any specific atom and can move easily from one atom to the next. Because they are free to move, they are often referred to as delocalized electrons. When the atom's outer electrons move freely throughout the solid, a metallic cation is formed. Each such ion is bonded to all neighboring metal cations by the sea of valence electrons, as shown in Figure 711. A metallic bond is the attraction of metallic cations for delocalized electrons. So here we have, right, the sea of electrons, and here in the center you have these metal cations, and surrounding them, right, just as you would suspect that you find your electrons, but these electrons are kind of like, think of like an ocean, right? And each of these cations are sort of like little tubes, right? Within that, the ocean flows underneath the tubes. And again, in this case of atoms, you sort of have these electrons just kind of floating from tube to tube, right? But in this case, these electrons are floating from cation to cation. And this is completely cool. This is what they do. This is kind of why the D block follows their own rules, etc., etc. So the physical properties of metals can be explained by metallic bonding. And again, can be explained by these sea of electrons. These properties provide evidence of strengths of metallic bonds. The melting points of metals vary greatly. Mercury is a liquid at room temperature, which makes it useful in scientific measurements such as thermometers and barometers. Right? Measures temperature, measures pressure, respectively. On the other hand, tungsten has a melting point of 3,422 degrees Celsius, and this is why they're used as light bulb filaments. They're usually made from tungsten, and they're also used in spacecraft, right? These things that can withstand high temperatures. In general, metals have moderately high melting points and high boiling points, as shown in this table to the left, right? 712. The melting points are not as extreme as the boiling points because the cations and electrons are mobile in a metal. It does not take an extreme amount of energy for them to be able to move past each other. However, during boiling, atoms must be separated from the energy of cations and electrons, which requires much more energy. Metals are malleable. which mean that they can be hammered into sheets. And they are also ductile, which means that they can be drawn out into a wire. Right? Figure 712 shows how the mobile particles involved in metallic bonding can be pushed or pulled past one another. Metals are generally durable. Although metallic cations are mobile in a metal, they are strongly attracted to the electrons surrounding them and are not easily removed from the metal. The movement of mobile electrons around positive metallic cations makes metals great conductors. The delocalized electrons move heat from one place to another much more quickly than the electrons in a material that does not contain mobile electrons. Mobile electrons easily move as a part of an electrical current when an electrical potential is applied to a metal. These same delocalized electrons interact with light, absorbing and releasing photons, therefore creating the properties of luster in metal. The mobile electrons and transition metals consist not only of two outer s electrons, but also the inner d electrons. As the number of delocalized electrons increase, so does the properties of hardness and strength. For example, strong metallic bonds are found in transition metals such as chromium, iron, nickel, whereas alkali metals are considered soft because they only have one delocalized electron, that S1 electron. Right? So this is what's kind of cool, right? When we're talking about metallic compounds, right? Metallic compounds, right? Think back to that sea of electrons. Right here, your red dots are your cations, whereas that blue is your sea of electrons. Right? Electrons are just kind of swimming throughout, swimming in between your cations here. And when an external force comes in and goes bang and hits them, right, we're able to go ahead and just kind of move those cations over a little bit, and they're still kind of cushioned by that sea of electrons. Again, this is how they are to make them more malleable and ductile. This is why we can go ahead and pound copper into a sheet and, maybe make some sort of instrument out of it. But you can't take sodium chloride and pound that out into a thin sheet. You'll just get a lot of dust. Due to the nature of metallic bonds, it is relatively easy to introduce other elements into the metallic crystal, forming an alloy. An alloy is a mixture of elements that has a metallic property. Because of their unique blend of properties, alloys have a wide range of commercial applications. Stainless steel, brass, and cast iron are a few of the many useful alloys. The properties of alloys differ somewhat from the properties of the elements they contain. For example, steel is iron mixed with at least one other element. Some properties of iron are present, but steel has additional properties such as increased strength. Some alloys vary in properties depending on how they are manufactured. In the case of some metals, different properties can result based on heating and cooling. Okay. And we look at 713, we have a list of alloys that you've probably come across. Right? Brass, bronze, cast iron, 10 karat gold, 14 karat gold, 18 karat gold, lead shot, stainless steel, sterling silver. These are all things, all alloys that you've probably seen every day in their various different uses. An alloy of titanium and vanadium is used in the bicycle frames that you see to the left, which gives it this really great strength. Titanium alone probably wouldn't be able to go ahead and withstand the impact of mountain biking, but once you start mixing in different elements in there, it really increases the strength. In a substitutional alloy, some of the atoms in the original metallic solid are replaced by other metals of similar atomic size. Sterling silver is an example of a substitutional alloy. In sterling silver, Copper atoms replace some of the silver atoms in the metallic crystal. The resulting solid has the properties of both silver and copper. And then there's also interstitial alloys. An interstitial alloy is formed when the small holes, or the interstices, in a metallic crystal are filled with smaller atoms. This best known interstitial alloy is carbon steel. Holes in the iron crystal are filled with carbon atoms, and the physical properties of iron are changed. Iron is relatively soft and malleable, however, in the presence of carbon, make the solid harder, stronger, and less ductile than pure iron. Section summary. A metallic bond forms when metal cations attract freely moving delocalized valence electrons. In the electron C model, electrons move through the metallic crystal and are not held by any particular atom. The electron C model explains the physical properties of metallic solids. Metal alloys are formed when a metal is mixed with one or more other element.